Okay. Yes. So we finished the topic convex sets. Now we will start with the functions, convex functions. Before that, I just want to leave some comments. Last time, I guess while we were discussing a proper cone here in solid set, I guess one of you asked a doubt or something, a comment where you were asking, is it a non-empty set? So I accidentally said in one or two sentences, I said it's a non-empty set or something. So that was a slip of the tongue. Okay, it is not. It need not be non-empty, but it should have non-empty interior. Both are different. Okay, for example, so if you consider a set like this set, a circle. Okay, so it only has the boundary, right? This set is non-empty, right? So this is non-empty.
With interior.
But it has no interior.
So you have to only consider with respect to interior.
Yeah. But no interior, right? So this so definition of solid set is with respect to interior points. But if you add a point here, okay, just one point, that will make it solid, right? Now it has non-empty interior.
Yeah,
right?
But it would not be convex.
Yes, of course. I'm just talking about what is solid set.
Yeah.
Okay. Yeah. So that is one point. Another point is we were defining generalized inequality with respect to a proper cone, right? Proper cone.
Yeah.
So then you may get a doubt, right? Why proper cone here? Why can't you use a normal cone, right? So why these conditions are necessary? So, but we don't have time to go into detail, but I can give you some hint. In detail, you have to read. Yeah, so for example, if you take this point, k is pointed, what does that means? K is pointed means if x is there, minus x cannot be there. It can happen only when x equal to 0, right? So why this is relevant here? Because if, for example, if you assume that both x and minus x are there, then let's say we say that x is less than y with respect to, it need not be vector. X and y can be anything. It can be a scalar, vector, or a matrix itself. So let's, with respect to this cone, right? What does that implies? Y minus x belongs to the cone K, right? This is the definition. But in that case, for example, yeah, here, what we are, if you assume that x and minus x are there, then you can also say that it can happen that x minus y is also can also belong to the cone, right? Then that means x is greater than or equal to y, right? So both cannot happen. Then that inequality is useless, right? So that is one hint for this part. And you can, like, for example, for this closed set, if you take R2 plus, so can I just so this is what R2 plus, right? So we are comparing x and y, but what happens if x equal to y? Then that has to be, this x minus y has to be this point, right? So if the boundary is not there, you cannot define equality here. Okay, so I'm not giving you the complete picture. This is some hint. Also, non-empty interior. mm, I don't know what one example where, yeah, maybe we can think about a cone. So yeah, I consider this as my cone. This is a cone, just right. It has non-empty interior, just a line. And then that means you can verify that. That means you can, in R2, you can only compare two vector. When you take x minus y, the first element has to be 0 because this has 0 y coordinate, right? So that has to be 0, and only you have an element here. So you are only comparing. So if you define an inequality like this, if you define an inequality with respect to this code, then that is useless for one coordinate. That all. So you can only compare two vectors which have equal first coordinate. Okay, so these are some hint behind these assumptions, but I also think that there are properties of generalized inequality. Uh, yeah, so here this is one property: x is less than y, u is less than v. Then you can add both right and left hand side like a normal inequality. So I asked you to read the properties from the textbook. I think some of the properties uh, are derived considering these assumptions also. Okay, but yeah, so that's it. We don't go into detail behind that because we have limited time. Yes, now we start with the next topic, convex function. So a quick recap, what we saw was in the first class, we saw the general framework of an optimization problem. Then we said that it can be a problem, optimization problem can be convex or non-convex. If it's convex, we are happy, right? So, and then we are now, what we are learning now is how to identify whether an optimization problem is convex or not, right? So then we saw that a problem is convex when a problem of this framework is convex when both the function and the constraint set are convex. So this was what we were investigating so far, the constraint set, right? So how a set can be convex. So we saw that if you pick any 2 points and draw a line, and the line segment should be within the set C, then only we can say that set is convex, right? So that's what we saw. Now we move to the objective function part, and we study why or how can we say, given a function, how can we say that it is convex or not. Yeah, one other comment is why are we interested in convex. We just said that we are happy for that, but what is some more formal intuition behind that. Because we know that a convex problem, uh, if you look into this graph, we don't know in detail at this point, but we know that this function look like a convex graph, right? So the problem, the advantage of convex problem is that they have, if you find a global, sorry, if you find a local minima, that should implies a global minimum. That will implies. That's why we are so interested in this guy, because here, like, so you have a, you know that you have a convex function and a convex set, okay, and you run algorithm and you got a point which is minimum. Okay, your algorithm identified a point which is minimum. So in this case, if the function is convex, that then you can easily say that with confidence, we can say that that is uh, that local minimum that your algorithm found is a global minimum that will minimize your problem. But what happens here? when you run, maybe you will get this point. So it's a local minimum. Then you cannot say that, right? So if you say this, if you say that, okay, I found this point, which is the minimum, then people ask, okay, but this function is not convex, or this is not a convex problem. Then how can you guarantee that it's a global minimum? Okay, so then this point is a suboptimal point, not an optimal point. Okay, so that's a key thing. So now we saw this set. Now we move to functions, right? So so this is more important, the concept of convex function, because often in our research, usually the set part is easy. Okay, you will have constraints like x greater than x less than 2, or something like a transpose x is less than 5 or something like that. So that you can most often you can easily identify, but function is a bit tricky. Function can take a very complicated form, and you should be confident, or you should learn we should learn some things about that in detail to identify that a function is convex or not. Sometimes the function can look very complicated, uh, with a very complicated expression. But if you learn, in this course we are learning many techniques, and which can help you to identify a very complex function. Within few seconds you can say that, oh, okay, this is convex because of this. Okay, that's what we are going to see in the coming lectures. So as we already did in convex sets, here also we will first define what is a convex function. How can you formally say that a function is convex or not? And then we will go through some operations that preserves convexity, and like how can you decompose your function into small functions and say that, okay, these small functions are convex, then I am composing bigger function using that smaller functions, and then I know that it's convex. So these are the learning process that we are going to see. Okay, so let's start. Definition. So when do you say that a function is convex? So we have a function which maps from Rn to R. This is our objective function. So we said that it is convex. First thing is domain of f is convex. Okay, the function should have a convex domain. For example, if I say that this is F, this is f of x, and this is my domain. Is it a convex set? The domain, yes, right? But what happens if I say that, okay, this is my function and this is my domain. This is my domain. Is it convex? It is not convex. If you pick any 2 points here, and draw a line between that point, that is not in the set, so that is not convex. So if you are given a function like this, without looking into the function, by just looking into the domain, you can say that, okay, this is not a convex function. Okay, so that's the first thing. Function to be convex, the domain of f has to be a convex set. Next one is, okay, my domain is convex set. Now what is further it should satisfy this inequality. So you pick any 2 points, x and y, from the domain, and form a convex combination, and evaluate the function at that convex combination that has to be less than or equal to the converse combination of function values evaluated at that point, x and y. Okay, so we will see what it is. So we have a function here, f of z is the variable. I'm just here, this is just in R, okay, for you to understand. Yeah, so I have the function, this red one. Now I pick 2 points, x and y. Okay, so what will be this converse combination between x and y for yeah, so when you take theta equal between 0 and 1 in this interval, including 0 and 1, you will get any points between x and y, right? So let's pick a particular point for a particular value of theta. So let this be the point. So this point is given by theta x plus 1 minus theta y. In that case, what I'm saying is, okay, now evaluate the function at this point, which is f of this combination, that point, right? That is this, right? So that has to be less than, now we consider function, the value of the function at the point x, f of x, and value of the function at the point y, f of y. Now what we do is we take the same uh, combination, converse combination, and find a point, right? So when you do this thing, you will get this point, right? What I'm saying is this point has to be less than this point. This is the formal way in which we can define a function. So then this obviously implies that a function like f in the form like a upward, right? I don't know what to say. Like, for example, this is convex. This is convex. So what about this? This is not convex because if you evaluate this 2 point, for example, a particular value of x, a conic combination. So this point is less than this point. Okay. So that's how we evaluate. We check whether a function is convex or not. So that is this definition. Okay. Yeah. And yeah, of course, we just throughout the discussion we focus on convex, but we can form similar arguments for concave function also. Then you have to reverse the inequality. Okay. So if f is concave, then minus f is convex. Basically, that means you can come up with a similar definition for concave function with just flipping the flipping the inequality. And now, okay, this is a definition of a convex function. Now, when do we say that if function is strictly convex? When this is satisfied with a, when we replace this inequality with a strict inequality. So this equal to symbol is missing here. So in that case, this is strictly convex. Okay. So be pay attention to the word strictly convex, because later we study what is a strongly convex function, okay, which is different. Strictly and strongly convex functions are different concepts. So this is strictly is easy, because strictly convexity is easy because you just need to consider the strict inequality. Okay. Yeah, so we saw that. Now we will see some examples of convex function. Yeah, so these are the examples of convex function. First one is an affine function, right? We already saw what is an affine function. So yeah, here we are considering example in one dimension in R. Okay, so it is an affine function is in R is ax plus b. How do you say that that is a converse function? Again, we check for the basic inequality criteria. We pick 2 points, take the converse combination, right? So what is f of x? It is ax plus b. We plug it here. Now, just I'm doing an adjustment. Instead of b, I write as theta b and 1 minus theta b. This will be b itself, okay? Right. Now just do some rearrangement, then you can easily get this guy, okay? But here, what you, for affine function, what you are saying is this left hand side is equal to right hand side. So then will it be convex?
Yeah.
Yes, right? Because it fits into this definition. But then what is the definition for a concave function? It will be this, right?
Yes,
So then will it be concave?
Yes.
Yes, right? So this is the only function which
That
is
is equal.
both convex and concave.
Yeah.
Okay. Yeah, so this is one function, and there are some other functions here. We are not proving it, we don't have time, but I will just show you how they look like. So first is an affine function, is a convex function, and next is an exponential function which has this shape. Okay, so this is convex, right? We can easily see this. Draw any line between 2 points that lies above the graph. And another guy is power, right? So what is this? X alpha. But important thing is that has to be, this function has to be in R++, means positive R, for that to be convex. And for not for any alpha, only for alphas which is greater than or equal to 1, or which is less than or equal to 0. So there is some example here, alpha equal to 3. Okay, so then this is x cube, and here alpha equal to -1, x raised to -1, which is 1 by x, right? So this is this guy. So is this convex? Yes, of course this is convex. Okay, this is also convex. Why are we saying R plus plus? Because if you consider x cube for entire R, then that will have the shape like this. Okay, in that case it's not convex.
What is the difference between R plus plus and just R plus?
0.
Okay.
It's like when we say
Strictly positive.
yeah. Also we use this notation for positive. This is positive semi-definite.
Yeah.
This is positive definite. Means
Yeah.
here the 0 is not included.
Yeah.
Yeah. So yeah, that's the usual notation we use in this course. If you have 2 plus, that means 0 is strict, more strict. Yeah. Yeah. Next is powers of absolute value. So here we know that x cube is like this. Okay. So one thing what we can do to make this convex is try to construct something like this. For that you have to take the power. Okay, so that is again uh, uh, a convex function for p is greater than or equal to 1. So you can try this. You can easily put such functions in MATLAB, right? So you can practice this, plot all the functions and see for different values p, alpha, and see how they look like. Yeah, so another important thing is negative entropy. X log x. You might have studied in information theory or some other course what is an entropy. It has some form like this, minus x log x. So negative entropy will be without this minus sign. So that will have a shape like this, which is again convex. So then that means entropy is a concave function, right?
Is there sign minus?
Yeah. Yeah, so that's it. Now we will see some of the concave functions. Yeah, of course, affine. We saw that affine functions are both concave and convex. And now again the power, the same guy here, but with a different value of alpha. So that has to be in R++ with alpha between 0 and 1. So this guy, okay. Here this is root of x, okay. This is a convex function because the line lies below the graph. Yeah, very important thing. Another log x. Log x is a concave function which has this shape. Okay, so this it's better you remember these functions because this often comes in our daily life. Then the moment you say log x, moment you see a log x, if you can say that okay, this is a concave function, then that makes your things easy. X cube in, yeah, so you are saying x cube in r minus minus, that will be concave function because that will look something like this. That will be concave function, right? So it's very easy to check a function is concave or convex in R because you just take the MATLAB and plot and see.
Yeah.
Okay, or just get some points, evaluate some point and plot and see. But this may not be always true. like if you have R10, if your function is R10, this is not possible, right? We cannot visually plot and see it. Then we have to learn other technique to check it. Yeah, so these are some functions, especially logx is very important. Now we move to higher dimension, Rn and M cross n. So yeah, so again, functions on Rn. First one is affine function. So affine function will be convex or concave? Both, whether it is in Rn or R. So here you can yeah. So you can make affine function in Rn or Rmn. Okay. So affine function. So in R, it is just Ax plus B. In R raised to Rn, it has the form A transpose X plus B. In Mn, this is like this is a matrix space where the function has this form, trace of okay. So this is how we define inner product of matrices. So matrix inner product between matrix A and matrix B is defined as. So here we have an inner product, right, between two vectors. So if you are writing inner product between two matrices, this is how we write A transpose X. So basically what it is doing is we have two matrices, pick the corresponding element, multiply those elements, and then add all. This is what it's doing. So that's like a definition of a inner product in the vectors, right? You pick corresponding point, multiply, and add everything together. So you can verify this, what this guy is doing. What is trace? It's a sum of diagonal elements, right? So you can just write two matrices A and X and see whether it's doing this what I said, doing the inner product.
Is this similar to like kind of linear programming? I don't know. Just seeing the
Linear programming.
yeah, like the inner product of A comma B, right? Like it's
Yeah. What I'm saying is this is an inner product. So, but how do you write an inner product between two matrices A and X? You cannot write A transpose X, right? This works only for vector. So for matrix, you have to come up with a new tool which is called trace. So if you can write this later. You pick two matrix A equal to A11 and X equal to X11, like you pick maybe 3 × 3 matrix and see what the trace is doing there. Then you can realize that it's doing this inner product. Okay, or this is simply you can write this in MATLAB language. This is what is this doing? This is picking all the vectors, all the elements from the matrix and forming a vector, right? This is simply equal to A transpose into vector A into vector B in MATLAB language. Right. Yeah. So what we saw was affine function, whether it is in Rn, or Rmn, that is both concave and convex function. So this is the only function which falls under both of this category. And now next is norm. Okay, all norms are convex functions. Okay, so you know how a norm is defined. So they are convex function, and the infinity norm also falls in this category. That is also convex. Basically, you can say that if p is greater than or equal to 1, LP norm with p is greater than or equal to 1, that is convex. But be careful if you consider a norm like x0 norm or x half norm, for example. These are not convex. Okay, but we already saw in the last class, this is not a proper norm. Okay, this is kind of it is called a quasi norm. When p is less than 1, it's a quasi norm. It doesn't satisfy triangular inequality. So those norms are not convex, but the proper norm where p is greater than 1 is convex. So this is very important. So this norm often comes in your daily life of research. Okay, so you will definitely come across this at some point where you have a function to minimize where a norm is important. Yeah, so that's important. Norm is convex. We also saw that in the set, convex set, norm bolts are convex, right? Norm bolts are convex and norm functions are convex. And another interesting thing is the singular value spectral norm. This is called spectral norm. So spectral norm of a matrix X is defined as the maximum singular value. Okay, so which is related to eigenvalue as this. So you have, if you are not familiarized with this topic, you should revise eigenvalue decomposition and singular value decomposition. Okay, these two topics. I think it's also given in the short description is given in the appendix of the textbook, optimization textbook by Bird. So you can revise that. Then yeah, only thing what we know at this, what we are saying at this point is, okay, I have a function of a matrix which is called spectral norm, which is the maximum eigenvalue, sorry, maximum singular value. This applies to eigenvalue also. Maximum singular eigenvalue, sorry, okay, singular value of the matrix. Okay, so we have this relation. If you have a matrix A and its eigenvalue, uh, to find its singular value, you can find the eigenvalue of A transpose A. I just write E value, okay, eigenvalue, and just take the square root, then you will get singular value. So you should be like aware what is an eigenvalue and singular values. Okay. Now we move up to next section. So one of the very useful way to check a function is convex or not is to restrict the function to a line. Okay, what does that mean? So we have a function f. Okay, a function f. It is convex if and only if another function g. We are making another function g. How are we making g? Just evaluate the function on a line x plus tv. Okay, so x and v can be any point, but that this quantity has to be in the domain of f. Then only we can evaluate f of that quantity, right? See here, we are evaluating f of x plus tv. Then x plus tv has to be in the domain of f, right? Otherwise, we cannot evaluate that. So if you fix any particular x, a particular x, and then we pick any arbitrary direction, any arbitrary direction v, okay? Then we form x plus v, then x plus, let's consider this as 0 for, okay, x is 0, then x plus v, maybe x plus 2v, x plus 3v, like that. And then you are evaluating the function on that line. So maybe I will show you a diagram. Here we have R2. Okay, you have x1, this is first axis, this is first axis, and this is second axis, x1, x2. Okay, and the function is plotted on the third axis. So this is my function. So what I'm saying is to evaluate, to see whether this function is convex or not. So pick any point x, okay, and just form a line. Consider any arbitrary direction b. Here this is v, and form a line using that. Okay, here I am picking x as 0. Then you can easily see that this x plus tv will be this line. Okay, then evaluate the function at that line. So what will happen here is when you evaluate, you will get a slice like this. Okay, so then see whether that is convex with respect to this line. That means with respect to t. So the new function, new function is on t, right? So whether this function is convex in t or not, we check that. If you find that that is convex, then you can say that our original function is convex. So this is very helpful in many places where we can, you have a complicated function, but you just evaluate that function on a line, and now you have a new function in t, and then you say that, okay, my gt is convex, then the original function is convex. Again, we are not covering the proof for that, for this, but yeah, here is an example. Yeah, this is an interesting example.
But you have to do it for every possible v.
Yes.
Yeah.
Yes.
Obviously, because otherwise
no, you take v as an arbitrary. Okay? You should not fix v. Okay. For any arbitrary v, if you can do this,
yeah,
then that's enough. So here we will see that we consider x plus tv without any with an arbitrary v,
yeah,
and we prove that that is convex. Okay. So then I say that, okay, I didn't make any choice for v. I took an arbitrary v, and then I prove that this is convex. That means my original function is convex.
yeah.
Okay.
If you don't pick one, it means for all.
Yeah, yeah. So I didn't make any assumption on choice of v, right? In that case, I can say that this is without loss of generality, my choice. Right? Yeah. So here is a function f of x equal to log of. So this is a function involving a matrix x. Okay. So function evaluated at this matrix x is log of determinant of x. So this is not a simple function. It's very complicated, right? First you have to consider, evaluate the determinant of the matrix, and then take the log. So whether this function is convex or not, it's very difficult, right? Maybe you won't be able to derive it using the general definition of convexity. It will be very difficult. So here we'll see what it is. How can we say this? Yeah. So like as we said, we consider we will make a function gt, which is log determinant x plus tv. Okay. So the important thing is x plus tv has to be in the domain of the original function f. What was the original domain of f? Which is positive definite. Here I'm saying that. Okay. In that case, because we have log here, so we want this quantity to be positive. Yeah. So then I can pick. I said I can pick any v x, but this has to be positive definite. That okay. That means if t equal to 0, what happens? So I can take any value of t, right? gt. I'm not restricting t. T can be 0, negative, positive, anything. It's a scalar. So when we say that so what I'm saying is x plus tv should belongs to s plus domain of f. So for t equal to 0, we have x. So that also should belong to s plus 1. So I cannot take any arbitrary point. That also has to be in this domain. Okay. So that's why we are writing here x has to be greater than or equal to 0, and v you can pick any direction, but together it has to be in the domain. Yeah. So then I pick this. Now just some mathematical step. Instead of x, I am writing this as uh, root x into root x, x raised to half into x raised to half plus t. Here I am introducing a new quantity, x half into x raised to minus half. This will be I, right? Identity matrix. Here also I'm doing this. And now what I do is I take x half out, like to the left side and to the right side. So right, I'm taking x half both the side. So here I will have I and t. So this I took outside, this guy also I took outside. So remaining I will have x minus half v x minus half. Yeah, now I have determinant of product of three matrices, like determinant A, B, C, which I can write as determinant A into determinant B into determinant C, which I am writing here. Okay. Now what is this? Yeah, again I have determinant of A raised to n here, right? Which is determinant of A raised to n, the whole raised to n. So I can take this half outside of determinant. That's what I'm doing. So I have two terms here, which I can multiply together and write as determinant x. Okay, and then I also have a product inside a log, so I can bring that outside the log and write it as a sum.
Okay.
So now I have log determinant x and log this quantity. Now, yeah. So next trick is here. So we have a determinant of a matrix. So this is our matrix here. So if I know the eigenvalues of this matrix, I can find the determinant. What will be the determinant? It's the product of the eigenvalue, right? So I assume that, so to find the eigenvalue, so I assume that this guy has an eigenvalue, lambda 1, lambda 2, up to lambda n. Okay, so what will be the eigenvalue of whole matrix? It will be 1 plus this t plus lambda i's. Okay, and product of that and log of this. Okay, next step. So this guy is safe, and here inside log we have a product. I take it outside as a sum here. So this is the final thing that we have. So this is what? This was our g of t. Now the thing is, now this is very easy. Now the thing is, I just have to see whether g of t is convex or not in which variable? In t, because g is a function of t, right? Is it convex? It's convex because we have a log here, which is, sorry, this is concave, concave. Okay, so we have a log which is concave, and then some of such functions, and then this guy is of no importance here. Okay, because it's not a function. We are checking whether the function is convex or concave in t. So this guy does not play any role here. So we know that this function is concave. So g of t is concave. That means the original function is concave. Okay. So this is an example in which we took a very complicated function and proved that it is concave by just evaluating that function on a line. Yeah. So here you again have the addition sum of concave functions here. So which we will soon see that sum of convex function is convex, concave function is concave. But we'll see. Next is another topic, extended value. Yeah, so extended value means you have a function f. For example, here I'm showing a function here, f, which has domain f, domain like this. Okay. Now what I'm saying is I can this is a convex function, right? I can make another convex function by considering all domain. Okay, all R. Here we are discussing a case in R. So just I can extend the function to all R. So what I do is outside the domain, I just assign that to infinity, the value of the function. So my new function, I'm just considering this as infinity. Okay, let this be infinity. And yeah, so the new function will have this form. Okay, so this function will also be convex. That's what we are saying. Okay, this is convex, right? You pick any 2 points and draw, but you should not confuse, because this is infinity. Infinity is involved, so you should not draw like this and say, okay, but now my function is not convex here, right? It's not like that, because this point is infinity. I just draw just for the sake of understanding. So to evaluate a point like at a point this, to evaluate our basic inequality at this point, you have to plug that value here. Okay, then this will be infinity, and here also it will be infinity. Okay, so anyway, what I'm saying is this: you can extend the function to undefined domain. Say that my f tilde is the new function, extended function, that is f of x when x belongs to the domain of f, and that is infinity when x does not belong to f, right? In this portion, it takes infinite values. Yeah, so then this has one-to-one relation. One is convex, then the other guy is also convex. So sometimes we use this concept. Okay, now we will take a small break. Okay, we will continue. So next is, we saw what is extended value theorem, extended value. Then next is first order condition. So we have first order and second order conditions for related to convexity. So here, so I will ask you to revise these two topics, gradient and Hessian. Okay, so gradient and Hessian. So let's say let's state the first order condition. So f is differentiable. First, before saying the first order condition, we should say that the function is differentiable, right? Then only we can say something involving differentiability. I'm sorry. A second. So when do we say that a function is differentiable? When the domain is open and the gradient exists at each point, right? So you should be aware of why this condition, because like in schools we studied, when we study basic differentiability, we said that okay, we can say that a function is differentiable only when its domain is open. If it's closed, for example, we are considering this function and I'm saying that both the boundaries are involved, then we don't know what is the differential of derivative of this function at this point, right? Because you cannot evaluate that left limit here, right? That's not the part of the domain, right? Only you can to check the differentiability, you have to evaluate that limit, right? Both left and right. So only if the domain is open, we can think about this. And second condition is gradient or derivatives exists at each point. So what is the derivative here? Here we are differentiating with respect to a vector, right? So then we, after taking the derivative, in this case, the derivative is called a gradient. That will give you a vector. Okay. So that you have to revise that. So basically it's nothing, right? But you just take the function, take the partial derivative with respect to first component of the vector x1. Second, like that, n component. So you will get a vector, right? And this gradient has to exist at each point. Now, what is the first order condition? So first order conditions say that first at any point x, the first order approximation of f is a global underestimator. So now we'll see what is a first order approximation. So there is a concept that I think you already know what is a Taylor series. So you have a function, f of x, and what I'm saying, I am expressing in Taylor series, f of x is expressed as this. So at a point, so this is the Taylor series evaluated or expressed at the point A. So what I'm saying is this function I can write as this. So the value of function at A, f of A, plus derivative of that into x minus a by 1 factorial into second derivative of that into x minus a square by 2 factorial, and like that. So what this will go up to infinite times. Okay, so if you consider all the times infinite times, then you will have an exact reconstruction of this function. Okay, so we'll see an example here. So here is an example. I'm considering this function f of x equal to e raised to x. Okay, so what is the Taylor approximation here? First, let's say 0th order approximation. That means you are just considering this first term. That means, and here I am picking the origin as a. Okay, so what I'm trying to do is express this function using Taylor series evaluated at a. So first I'm picking the 0th order approximation. That means just discard all other terms, just pick this guy. So f of a, right? So what I'm saying is my approximation for this function is f of a, that is f of c, e raised to 0 equal to 1, right? So I approximate this function with this guy. So I'm saying that this is my approximation. So this is a very bad approximation, right? Because we just pick only one time. But you can say that when the approximate when you consider the value of approximation uh, or Taylor series close to this point where we evaluated the Taylor series, then it is, the error is less. At exactly at A, it coincides. F of the function and approximation coincide. But as you move further from A, then the error is high. Okay, error become high. Okay, so near to the point where we evaluated, it coincides with the original function value. So we know that this is a bad approximation. Now the second thing is take the first order. Okay, x raised to 1, first order. So just this two time. Then you can just plug that here. You can just evaluate this expression, and then that will be 1 plus x. So then this first order approximation of e raised to x will be like this. Now, if you go for a second order approximation, you just plug that a equal to 0 here and take this 3 times here. Then that will be this guy. Okay, so as you increase the order, then you will get more you get better approximation. So here again you can see that the error will be lesser compared to its previous order approximations. Okay, so that's the concept of Taylor series. Okay, that's it. Now what I'm doing is I'm interested in first order approximation here. That means I pick the points up to this. Okay, so what you do is you have a function. So now I am explaining everything in R. Okay, so but this applies to R raised to n, R. Okay, because there we have gradient. So but it is easy to explain things in R. We are familiarized with that, right? So I'm explaining with respect to R, in R. So I have a function f of y, okay, in y, and so I pick a point x, and what is the value of the function at x? It is f of x, right? Now uh, I will take an approximation, first order approximation of this function evaluated at x. Okay, that will be f of x, like how do we say here, f of a, instead of a we are considering x here, f of a into first derivative into y minus x. You can see this into first derivative into y minus x. So basically yeah, so basically this is the this is the equation of this line.
Mm.
Okay. Yeah, you can also get the equation of line from this 1 point formula that you learned in high school. In this case, like you have a point here, f of x here, and a slope, right? Then you can get the equation of the line. Yeah, so now what I'm saying is, yeah, so the main part is this. Okay, I have this guy, this line. Now then what I can say is that this line will always be less than or equal to the entire function of y. Okay, so this is very useful because what, so only information we have, just have local information at this point x. We have local information. What is the information we have? We know about f of x and we know about f dash x. This is the only thing that we know at the point x. But what we are, by forming this inequality, what we are obtaining is, using local information, we can get a global conclusion, or a global, a global, this is a global statement, right? I'm saying that this, with just this two information, I'm saying that my entire function is above this line. Okay. Okay, so this is very, very useful. Okay.
What about the second order integral? If it comes in second order,
You can expand.
then still it will be less than or equal to f of x.
No, I'm not saying that. I'm saying only about the first order. Okay. Yeah. So that this is the first order condition. Yeah. So yeah. So what does it say is that? So, but this is true only for convex function. Okay. So if you consider another function, for example, yeah, or I will just draw on the, what happens if the function was something like this. You cannot say this, right? So only for convex function you can say this. Yeah, so what is first order condition? It says that first order approximation of f is a global underestimator. So this guy will always falls below this graph. That's what this equation is indicating. Yeah, so this happens only if f is differentiable with the convex domain. Yeah. Now we move to second order condition, where we have, so for the first order condition, we should have a differentiable, f has to be differentiable. In second order condition, this is,
First order could be differential.
yeah, so don't get confused here. I was just talking about Taylor series. So in that, if you say second order approximation, it will be this. But this second order condition has nothing to do with Taylor approximation. But we are just, this order means it's just a second order derivative. Okay, we are making some statement using the second order derivative. Okay. Yeah, so second order condition, for that, what is the criteria? Of course, f has to be twice differentiable and domain has to be open as usual, like for derivative text. Then what we can say that the Hessian is a matrix, second order derivative, or you take gradient, again gradient, then you will get a matrix, right? So what is the matrix looks like? It will be like this. Ij, the entry of this Hessian matrix, will be this dot square partial derivative, second derivative f of x with respect to xi. It's basically like you will have a matrix and This is ith row, and this is jth column. So that will be this guy. Okay, so like that you form all other elements. So that's a Hessian matrix. So now, if this is twice differentiable, that means its domain is open, and this matrix, Hessian matrix, exists. In that case, now we will see what is second order condition. F is convex if and only if this Hessian is positive semi-definite. Okay. Now, when do we say it is strictly convex? Just drop this equality here, make it a strict inequality. Then it is strictly convex. Yes.
So, yeah, that has to be Sn plus to belongs to cos square.
No. What I am not at this point. I am not yet at the second order conjugate. Here I am saying. So here this is a general statement for a function to be differentiable. I mean, here what I'm saying is what is whether Hessian exists or not. Okay, so I'm not yet at this point. Okay, here I'm stating the second order condition. Okay, so of course here that has to be positive semi-definite. So now if you have a function, then you take two derivative. It's not derivative actually. You take the gradient and the gradient again and form the Hessian, then examine whether that is a PST or not. Yeah, so one interpretation of this second order condition is, let's consider an example in R. Okay, you have a function like this. So then now you just draw the tangent at consider different point x1, x2, x3, x4, x5, and draw the tangents. Okay, what will be the slope of the tangent? It will be slope of a tangent. It will be f of x, derivative of f of x, right? I'm just considering an example in R. So now we can say it's a derivative, right? Now, what I'm saying is, in the second order condition, what I'm saying is f dash x, f double dash x should be greater than or equal to 0. Okay. So when you say that, if you have a non-decreasing function, for example, g is non-decreasing, okay, and then we can say that g dash should be greater than or equal to 0. Okay, so here then what we can say that I have a function f dash x. Initially I had a f of x. Now I have f dash x. Now I'm saying that the derivative of this f dash x, that is f double dash x, is greater than 0. That means f dash x is non-decreasing. So slope of the tangent increases as x increase. It's not increase. You have to say non-decreasing. Okay, increasing and non-decreasing are slightly different, right? I hope you know. For example, this function is an increasing function, but if you consider something like this is a non-decreasing function. Okay, this you cannot say that this is an increasing function, but at this point this is not increasing. Okay, so this is non-decreasing and this is increasing. Okay, so here I am putting this in.
Is it correct to say slope of tangent, because tangent of a function itself is a slope?
No, tangent is no, tangent is this line, right? So
Yes.
the slope is the derivative. For example, at x4, the slope will be the derivative evaluated at x4. Okay, so that's why I'm saying that f dash x. Okay, now you are taking again a derivative. Okay, and then that is greater than 0. That means this guy is an increasing function. That's what I'm saying. Yes.
I guess what he meant is that slope and tangent can mean the same thing in this context, because your tangent that you draw is also the slope of the function. But because you formulate it as the slope of the tangent is increasing.
Yeah.
And
Mhm.
so it is, but it is just, if you know how
Yeah,
it's
so-
defined, it's fine, but the words can mean the same thing.
Okay.
depending on the
So what I'm
context.
saying is, pick at
Yeah.
the point, for example, x1,
Yeah.
draw the tangent. You have a slope, right?
Yeah.
And x2, you have a slope. And this slope for a convex function increases. Here you can say like you have a slope like this, and here this slope is increasing. Here slope is 0, increasing, again increasing. Okay, so from left to right, it keeps on increasing. That's yeah. So just a second. Yeah, so that's a second order condition. We have a nice interpretation here. And now we move to an example from the using the second order condition. Yeah, we have a quadratic function here, which is expressed as this x transpose px plus q transpose x plus r. Okay, you may often come across a quadratic function. Maybe I have encountered this in my research. There was a quadratic function. Yeah, so then my question is whether this quadratic function is convex or not. In general, like in a one-dimensional, in R, if you take, for example, x square, that is quadratic, right? I mean, sorry, that is convex, right? But what happens if you take minus x square? That is not convex, right? But now we extend this. In general, you have a quadratic like this, a quadratic expression like this, whether this is convex or not. You cannot say that all the quadratic functions are convex. For that, here we use the second order condition. Take the gradient, okay? Then you will get this guy. So I suggest you, maybe you are aware of this. There is a book, there is a small document called Matrix Cookbook, where you can just search this, Google this, you will get this, where you can get this like this kind of formula where what happens if you differentiate this with respect to vector x, double differentiate, what happens, and many other things related to metrics. Okay, so this is very useful. If you have any doubt while evaluating the derivative or gradient of this, you can refer to that book and see. Yes. So yeah. So when you take the gradient, you get this. Again, take the gradient, you will get p. Okay. Then now what we are saying, what we established before was, for a function to be convex, this has to be positive semi-definite. So then we can say that a quadratic function expressed in this form is convex only if this guy is PSD. No matter what is this guy or this guy, that's not our interest. Take the quadratic term here, second order term here, and see the matrix. It is difficult because because for that, I don't know. You have to evaluate this thing at every point and check, right? So how do you do that? I don't know. It's difficult. So usually you don't. First order condition gives a nice global estimator, but to check convexity, it's difficult to use that. So second order condition, take two differential two gradient and just make it. Yeah, so that's it. So we know what now. If you have a quadratic function, you should say that, okay, my matrix P in the quadratic term is PSD, or yeah, PSD. That means it's my function is convex. Now, next example is this. We already saw least square x minus b. So you can express this as x minus b transpose ax minus b, take the derivative, go to this book and see if you're struggling, go to this book and refer to that, take the derivative. So then the first, so sometimes I say derivative, but it should be understood as gradient. Okay. So yeah, so here we have gradient and here we have Hessian. So this matrix will always be positive semi-definite. So yeah, so then irrespective of what a and b is, this function will always be convex.
The v square of the two function, it will be like modulus of ax minus b, right? If it's like norm 2 whole square, it is like modulus of x. It's like
Modulus.
root of ax minus b whole square. So it's ax minus b.
It's not square. Here we have vector. So
Like
you take each component. For example, when you what is this guy? This guy here. This guy here is x1 square plus x2 square, like that. Okay, it's not just it will be absolute value for when x is in R. Okay, and then if you remove this, it will be like this. What's the doubt?
Okay. So because I think A is a matrix and it's
Okay, here x is a vector, A is a matrix. So this guy will be a vector. Ax will be a vector. B also will be a vector. Okay. Yeah. So the my point is, no matter what is here, this quantity will always be PSP. This you can verify. You just plug in x transpose, A transpose, A and X, and just evaluate, and you will realize that this always will be positive or zero. Okay. And now, so this is another one, first one, second one, and third one, quadratic over linear function. So this is this function. So it's not trivial by seeing this function to say that whether this is convex or not. It's not trivial. So what we just take the Hessian. So here we have gradient and Hessian. Okay, this you can rearrange like this. Okay, and here you have like an outer product here that will be positive for y greater than 0. Okay, this part will be PST, positive semi-definite, but we have a y cube, so we have to make sure that y has to be greater than 0. Okay, so this is just a matter of expanding and rearranging things.
just
Yes,
like I'm just wondering how that came into 2 cross 2 matrix.
this one,
No, like the second step.
this one.
So, yeah.
So that's why I'm saying here
Gradient of the gradients.
revise these things. Okay, gradient and Hessian. So just a quick thing. So first, what you have to do is quick explanation. Differentiate this with respect to x and y. So this is with respect to x. This is with respect to y. Now what you have to do is take this row, take this guy, differentiate with respect to x here, and with respect to y. When you differentiate with respect to x, you will get a 1 cross 2 matrix, right? Or 1 cross 2 vector. Again, when you differentiate with respect to y, you will again get a 1 cross 2. Stack that together and form a matrix. Okay. So it's like a x, y, then again, then you have 2. Then this 2, you again x and y. Then you have 4. Okay. So that's the definition of Hessian. Yeah. So then you just rearrange this as a product, and this is an outer product, and means it's like A into A transpose. This will again be a PST, and for any y greater than 0. Yeah, so this is this function. So this is very helpful, the second order condition. We cannot simply by simply looking into this, we cannot say this. And yeah, another example is a log sum exponential. So you have log, inside that a sum of exponential. Okay, this is called a soft max function in some field. Why? Because, for example, you have x1, this guy to be 1, 5, 10 or something, then you are taking exponential of this, okay? And so in this sum, of course, this guy will dominate, right? You have 1, 5, 10, then you are raising that to, you're taking that as a power of e, right? So now this will be very large compared to other guys. And then you are taking sum. So of course, this guy will dominate. And then you take the log of that. So you will get something close to 10. Okay, so this is this function, what it is doing is kind of finding the maximum in a soft way. Okay, so this is called soft match. And yeah, so the thing is, how do we examine the convexity of this? So again, yeah, so this is a, you can see this, I am not explaining everything. So we have a function here, take the gradient. So when you take the gradient of, so you have a log here. So when you take a derivative, that will comes as the denominator, then you will have this thing. This I am calling this guy as a vector z, and then this is equivalent to z by 1 transpose z. And then take again the Hessian. So I'm not explaining everything. You can just later see what is happening here. And then we will write like this, and here we can reduce this into this guy here. Okay, where now we have to examine whether this is positive or not. Where this guy is always positive, so you can discard this for checking whether it's positive or not. And then you have something like this. So here we have a inequality, Cauchy-Schwarz inequality, which says that if you have two vector u and v, you take the inner product of that and take the absolute value of that, which should always be less than or equal to the norm of those two vectors. So this is valid for any norm, but here we are considering two norm. Okay, in this special case. Now, since you have this expression, you consider a u as z half, z1 half, z2 half, raised to half, I mean, and v as z1 raised to half, v1, like this, and just see, then you can see that, and just apply this here, then you can see that this term is bigger than this term. So this will be positive. So this will take time to explain, but you can just see I have written every step. You can later practice here. Okay, yeah. Another guy is a geometric mean. This will this is a concave function. Okay, it has a similar proof that we are skipping now, but you can practice this or try to prove this, something similar. Yeah, so what we saw was, we saw first order condition and second order condition. First order condition use a global underestimator. Second order condition says that to check whether a function is convex or not, you take the Hessian and check whether it is positive semi-definite or not. Now we move to another concept, epigraph and sublevel set. So first, sublevel set. We have a function f from Rn to R, and now what is an alpha sublevel set of that function? So which is denoted, this is denoted as C alpha sublevel set of a function, which is a set such that it's a set X such that X is, of course, X has to belong to domain of F, and function evaluated at that X should be less than alpha. So it's very simple. You have a function here. So this is f of x. No, my sublevel set C alpha is X belong to domain of such that f of x is less than alpha. So let's consider this alpha, and the sublevel set corresponding to this alpha is all the x which gives like, you understood, right? That will be this. So you pick all f of x which falls below this line alpha. So that will be these guys. and then find the corresponding x, and then form a set. Okay, so here you have alpha, f of alpha, sorry, f of x equal to alpha. Here, at all this point, f of x will be less than alpha. So take all those x here and form a set. So this set is the sublevel set. Now what we are saying is sublevel sets of a convex function are convex. So if you have a convex function, always the sublevel set will be convex. Here we have the C alpha to be convex, right? So it's not possible to think about a convex function which is having a non-convex sublevel set. Okay, but converse is false. So you can have a sublevel set convex, but the function not convex. Can you say an example? Huh?
The
No,
sublevel set is it is not a convex function, but the sublevel set is
yeah, that's correct, I guess. Yeah, you take x cube
minus
and
1 to 1.
minus 1 to 1, okay, and pick any sublevel set, and the less than 1 will be a convex set. That's correct. Or yeah, that's correct.
What's the requirement for the convex function? Not that the domain, that it is an over.
I don't get your point. What is the requirement?
And if you, I don't have the slides here. If you go a bit up,
Mm-hmm.
where you defined where it was, because now you include the edges for which you don't know the derivative. It doesn't matter.
Okay,
It's
so
only for the first or second order. It's only a
no,
requirement.
here I'm not talking anything about second order condition. Okay,
Yeah.
so you cannot always come up with this idea. Like, for example, you can even have a function like this, which is not differentiable,
Yeah.
but which is converse. In
Yeah.
this case, you cannot come up with this second order condition, right?
You just
So
do it
what
in a
I'm saying
different
is,
way. Yeah.
if you want to use that second order condition, then the function has to be differentiable, and for that it has to be open.
Yeah.
Okay. But this is not useful in all the cases.
For example, this one.
Yeah.
Because this will be closed.
Yeah, so you cannot find the derivative if it's closed. Yes. Yeah, so yeah, what we are saying, yeah, about the converse. So for example, if you have a function like this, is this convex function?
Yeah.
Okay. No.
No, it's not differentiable.
Okay.
Yeah.
So if the function is differentiable and the second derivative is greater than 0, okay, that is convex. It doesn't mean that if the function is not differentiable, it is non-convex. I didn't say that. So for example, absolute value function, which has this shape, this is a convex function. But is this function differentiable? It is not differentiable at this point. Okay. So be careful. We said differentiability, it's a way to check convexity. It's one of the way to check convexity, but there can be functions which are not differentiable. Okay. Yeah, so coming to this function, is this function convex? No, this is not convex. You pick any 2 points, just draw a line that is below the graph. Okay.
Yeah.
But if you take an alpha sublevel set of this, for example, I consider alpha here. The sublevel set will be this guy here. That is a convex set, right? So we cannot say that if the sublevel set is convex, the function is convex. This we cannot say. But if the function is convex, then the sublevel sets are convex. So it's only applicable to one direction. That's why we are saying that this is false. Convex is false. Yes.
Why their function is not convex?
This function.
The V shape.
This function. You pick any 2 points. So for the function has to be convex. You pick any 2 points. Draw a line that has to be above the right, above the function. But here, if you pick any 2 point and draw a line, it will be like this. It's
No, I'm
below
saying the V shape.
this function.
Yeah, it's not really convex because it still has this concave curve.
Sorry, I didn't get it. Which function are you talking
The
about?
third
Down one.
This guy?
Yeah.
This is a convex
is
function.
convex.
Okay, this is an absolute value function. This is a convex function. Okay, what I'm saying, what I said that this is not differentiable. Okay, so my point here was, if the function is not differentiable, you cannot make a conclusion about its convexity in general. Okay, but if a function is differentiable, then you have to go for a second order derivative and check whether it's positive or not. Okay.
Yeah, what I refer to, I thought you were talking about the green box in the rightmost function, because that's still not convex, I would say.
It's
Just-
not convex.
Just by the way you draw it, yeah. So the sublevel set is not convex.
Sorry, it's alpha level, alpha sublevel set is convex, right?
Well, it doesn't look like that.
Why? Because so alpha.
Because you can still draw 2 points.
Okay.
Yeah, it still
you
has
see-
this concave
You see my
shape.
opinion.
Oh, okay. So
you-
you, so I have a limitation in drawing, right? So this has to be. So you mean this has to be very, very smooth? Okay, I'm drawing something like this. Okay, is that your point?
I was talking about the green box, I guess.
Yeah, but whatever is within the green box is still not a convex function.
Why? It's not within green box. Like maybe you took it wrong. What I'm saying is, what is a sublevel set here? You pick any
Oh,
alpha.
yeah,
Okay.
sublevel
In
set.
that domain.
Yeah, yeah,
Whatever the
Okay.
points are there.
So-
in
The
the
so-
domain.
set is convex.
yeah. You pick any alpha here. So
Yeah, okay. I'm
You got it?
mixing up set and function.
Yeah.
So you're claiming the set is
Set.
convex. Yeah.
yeah. So that's a
Yes.
definition. So sublevel set is a set.
Yeah.
Okay. Where f of x is less than alpha. So sublevel set is associated with alpha, C alpha. How do you form that? Go to domain, pick all x such that f of x is less than alpha. So in this case, it will be this guy, this part. Okay. Okay,
Thank
no
you.
problem.
Yeah.
Now, epigraph. So epigraph is another concept where, again, this is a set x and t. Now you are adding one extra variable t. So again, that of course will be in a higher dimension, n plus 1, okay, such that x belong to domain of f. So we have a set here, we have a vector and a scalar here, such that x belong to domain of f, and f of x is less than t. So that means, what does that mean? So pick this graph. So this is my f. Okay. So what is the epigraph of this? So pick a particular x here. Okay. Yeah. And then consider all t such that t is greater than f of x. So what is f of x here? It is this point, right? So consider all t which is greater than f of x. So that will be this guy. So if you pick a point x here, all the guys, all the t's which is greater than f of x, that is this value here, will be this way. So form like that. So then basically you have a graph, a function. Whatever is above that will be your epigraph. Epi means above, right? So for example, you have a function like this. So it is defined just for this interval. So epigraph will be all these guys.
Yeah.
This region, that will be epigraph.
And the claim is that the function is convex on if and only if the set
Set epigraph is convex.
is
So be very important, these two concepts, alpha sublevel set, epigraph, these are sets. Actually, it gives sets, right? So this is a set, and this guy is also set. Yeah. So now, do we have time?
Oh yeah, a bit.
5 minutes, 10 minutes, 5 minutes. Okay.
Yeah,
Let's.
I should start quarter plus one. My next session.
Okay. So I will take
So 5 minutes.
maybe 5 minutes. Yeah. So next is Jensen inequality. So here, so this is a new concept, new topic, Jensen's inequality. So we start from the basic definition of convexity. This is the basic definition of convexity, right? But here, what we saw that here we have two points xy. But let's consider let's take a case of many points, xn points. Okay, so the definition of convexity still we can form, right? So we have theta i's. This should be less than or equal to this guy here. Okay, but only condition is theta I has should add to 1, and that should be between 0 and 1. So this was the case where we only have 2 points. Here we have n points. Now the moment you see this, you can think about one picture that may come to your mind is, okay, you have some variable which adds up to 1 and which takes value between 0 and 1. So is it similar to something that you learned? Probability distribution, right? Probability distribution values, that has to be, when you integrate that, or for a discrete probability distribution, when you add that should add to 1, and probability always take value between 0 and 1. Okay, so now I am extending this to infinite point cases, where I'm saying that I have x here. Instead of this weight, I plug in the probability distribution here, integrate it. Basically, it's doing the same thing for infinite points. Okay, so f of that guy is less than or equal to. Here, what I do is I take the I have f of x, and instead of the weight, I have the distribution, and then integrate it over the domain of f. Okay, so this is I'm just extending this inequality to an infinite point case. Now, what is this? This is the expectation of x with respect to this probability. So I can write this is f of expectation of x is less than or equal to. What is this? This is the expectation of this function, expectation of f of x. So this is called Jensen inequality. Remember, this is for, we stated this for convex functions. If you consider if you apply Jensen's inequality for convex function, then we start from here, right? So this should have the opposite direction. So just remember one case, for example, convex case, and if you forget what it is, you can just easily derive from this. Just write the inequality of convexity, and just here also, from here also you can write, for example, a basic inequality is a special case with a, let's say we have a discrete probability distribution, where this is the probability, one probability, and this is the other guy. So what is this? This will be the expectation, right, or average. So it's kind of an average, right? So we can write this as expectation of x less than or equal to, this is the average of the function values. So this is the expectation of f of x. So from this definition of convexity, you can easily get the Jensen's inequality. Yes, maybe it's a good point to stop.